In this video, we're going to actually look at some specific examples of some important kinds of conjugate subgroups. The very first one that I'm going to do is a really basic one, and it's just one that people need to kind of be aware of. So we're going to let G be any old group at all. And we already know that the set containing just the group identity is a trivial subgroup of G. And it turns out that the conjugate subgroups of this particular subgroup are not very interesting. If I look at a conjugate subgroup of this particular subgroup, I wind up getting the set of G inverse EG, and that's just the set containing G inverse GE. That's just going to be the same set itself. So in other words, the trivial subgroup containing just the group identity doesn't have any distinct conjugate subgroups. They're all just equal to the subgroup itself. Well, if G itself is a subgroup, so it's also worth looking at. Let's make our subgroup equal to the whole big group. And in this case, if I pick any G inside G, that G is also going to be inside H, and so G inverse HG is just going to be the set of G inverse H times G, where H is running through all the elements of H. But since G itself is inside of H, which remember is equal to all of G, then this product that we're looking at, this guy here, is just some element of H. In other words, it's some element of G. So since we are assuming that H and G are the same thing, G inverse HG is just some element of G, which happens to be H. And so what this says is that G inverse HG is, lo and behold, all of H, which is all of G. So the trivial subgroups, remember, trivial subgroups are this guy and the whole group itself. Well, the trivial subgroups have the property that any conjugate subgroup of them turns out to be just the subgroup. So if H is equal to this, or if H is equal to the whole group, then the conjugate subgroups are just the subgroup itself. There's nothing very interesting going on there. Well, now what I want to do is I want to look at two kinds of subgroups that were introduced back in Chapter 3's exercises. So the center of a group G is written as Z of G, and Z of G is just the set of everything inside of the group, such that it commutes with all other elements. So in other words, you get into the center by commuting with everybody. So if a particular element belongs to the center of G, and we look at any other element of G, then we automatically know that GA is going to be equal to AG. That's what being inside the center means. Well, let's see. What would the conjugate subgroups of the center look like? So what are the conjugate subgroups of the center of G? Well, let's see. Let's just let A be some element of G. And what I want to do is I want to look at the conjugate subgroup A inverse times the center of G times A. Well, A times A is going to be what set? Well, let's think about this. So I'm going to just kind of put some question marks there. I do know this, that if I take something inside the center Actually, let me change my notation. If I take something inside the center of G, then A inverse B is going to be A inverse, and I'm also going to have B times A will be A times B. So let's see, what can we say over here? Well, we get this idea. If we pick some element, and let's see, I'm just going to call this element C. If C happens to live inside the conjugate subgroup, A inverse times the center times A, then we're going to get this kind of lovely little thing. C is going to be equal to A inverse times something in the center times A, and this is for some B inside the center of G. And what that's going to say is that C is going to be equal to A inverse times A times B. This is because B is inside the center of G, and the center is everything that commutes with everybody. And so this winds up being E times B, which is B, which is inside the center. So what we now know is that the conjugate subgroup, the conjugate subgroup is clearly a subset of the center. Well, it doesn't take a whole lot to realize that the thing goes the other way. So let's get that as well done. If I take something inside the center of my group, then we can write things this way. B will be equal to E times B, and that E can be written as A inverse times A times that B. And now because B is in the center, we can swap the order of these two elements because B is inside the center. So we can write that as A inverse times B, and that's going to be inside of our conjugate subgroup. And so what we now have is the center is also a subset of the conjugate subgroup. And if we look at what we've done, this inclusion and this inclusion, those two facts together, are going to say that the conjugate subgroup for the center is just the center itself. So the net result of this is that any conjugate subgroup for the center of a group is just going to be equal to the center of the group. And that equation is going to be true for all A inside of the whole group. So centers are not very interesting. Their conjugate subgroups are just the same as the certain things. So I want to state that very clearly, because what we've actually done is we've actually proved the following theorem, and the following theorem can be stated very cleanly as if we take a group and we take any element inside that group, then the conjugate subgroup for the center with that element, so A inverse times the center times A, is just going to be the center again. Well, the final thing that I want to look at in this video is another idea from a subgroup that was introduced back in the exercises in Chapter 3. And so this is coming from exercise 53 in section 3.4 introduces the notion of the centralizer. Now, the author introduces the idea of the centralizer of a set, and in particular a subgroup. But I want to start with the definition of a centralizer itself. We did go through this before the break, but it's been a while since we've dealt with it. So let's let G be a group. And we're going to let A be any element inside of G. The centralizer of A is going to be written as capital C parenthesis little a. That's the centralizer of A. And we're going to define the centralizer of A to be every guy inside the group such that A commutes with that particular element. Now, centralizers are different than centers, and it's got to do with the order of the quantifiers. To get into the centralizer, you have to have a specific A specified, and you commute with that particular A. To say something is inside the center means you commute with everybody. And that's actually something that's probably worth writing down on its own. So let's go ahead and do that, because a lot of students get confused between centers and centralizers. So X inside the centralizer for an element means X does commute with that specific element. So X commutes with the specific element named A. And in particular, all of the powers of A are always going to be in the centralizer. So it's worth noting that A to the K is always going to be in the centralizer of A for any A inside of a group G. Likewise, you commute with your inverse, so the inverse of A is always going to be inside the centralizer for any A inside G. And putting these two things together, your negative powers are also always going to be inside your centralizer. The center, on the other hand, so let's actually do this in a different color. The center of G is the set of things in G that commute with everybody. So it's any G in G such that Gx equals Xg for all X's inside G. Now, to kind of make the quantifier a little bit more clear, what I'm going to do is I'm going to change this definition ever so slightly. That X is a dummy variable. I am going to write that dummy variable with an A. So it's going to be all of the G's in G such that GA is equal to AG for all A's inside of G. So the center has a universal quantifier in its definition. That is a universal quantifier that's buried in the definition. And up here in the centralizer for a particular element, that we are doing this with respect to a specific element, that is an existential quantifier. You get into a particular element, you get into a particular element's centralizer by commuting with that particular element. You get into the center by commuting with everybody. Now, it is something that I do want to point this out as a straightforward idea. it is easy to show that the center of a group has to be inside of the centralizer of any element. And since all of these guys are subgroups, I'm going to say subgroups. So the center of G is a subgroup of the centralizer of A for every A inside the whole group. So what we want to do next is we want to generalize the idea of a centralizer for a particular element to the centralizer for a whole subset, or more importantly, for a subgroup that is part of some kind of non-abelian group G. So the centralizer of a subgroup H is going to be the collection of all of the G's inside our group G, such that G times H is going to be equal to H times G for all of the H's inside our subgroup. And so basically saying that X belongs to the centralizer of H says if I pick any element of the subgroup H, then we know XH and HX are exactly the same thing. Now, this brings up an interesting question, and I want to look at it this way. If X is inside the centralizer of a particular subgroup H, then it turns out that the conjugate subgroup X inverse times H times X is going to have to be equal to just the subgroup H itself. And that's something that is pretty straightforward. The reason why this is so is that this set here is X times H times X, where H is running over all of the H's inside H, but X is inside the centralizer of H, so we can swap the order of two of those guys, and when we swap the order of two of those guys, actually that one should have an inverse on it, we're going to get H times X inverse times X, where H is inside H, and this of course is just E, so we're now looking at the set of H's such that H is in H, and that's just a fancy long-handed way of writing the set H. So when X is inside the centralizer, the conjugate subgroup for X inverse times H times X, that's just going to be the subgroup itself.